Okay, so we're over here, and of course, we've done and we have solved the problem using some heuristics. However, practically what will happen is that I'll still backtrack, and not once but many times, which means I'll lose out on computation. Now, my question over here is that if a branch is to backtrack, that means out of all the values which the current variables have, there's some inconsistency, there's something wrong. Otherwise, why will a branch backtrack? So can I just look at a partial graph and say there's some inconsistency, there's something wrong in the value assignments, and say that because this graph will backtrack, let me backtrack immediately. Why go around, do all those calculations when I could just predict that an inconsistency will eventually make the entire graph to backtrack? So that's what my mantra around over here is. Before I do this real backtracking, can I make some inference, say I, and only when that says that, hey, I looked at it, I did not find any inconsistency, then I make a call to this, because this is computationally expensive. Can I predict that up? Of course, I will add I to my current set of inferences. And if you're adding something, you might remove I as well. If it still backtracks, it could still backtrack. So can I guess? Can I check for consistency and say this branch will backtrack, and therefore do not even call this thing up? That's going to be my next little session on. Now, it turns out that if you want to make the graph consistent, let's apply the simple thing. Let's make the vertex consistent first, also called as one consistency. This one means I'm checking for the consistency of my entire graph by looking at just one node all the time, also called as the node consistency, because I'm looking at just one node, which is the vertex, and saying, is this consistent or not? And a vertex with some domain is not consistent if there is a unary constraint that's stopping it from being consistent. So of course you would delete this up and say, hey, that's consistent. Excuse me, we've already done that, so no need to worry about it. You've already taken care about it once, and you do it once before you start the solution. Remove all the unary constraints. Your graph is and will always be node consistent. So let's go one level deeper. And by going one level deeper, let's see if I can really get in something out of it. So let's look at two vertices which have an edge. So I've got a A, I've got a B, they cannot take in the same values. And let's say this is red and this is, let's say, a R and a G. And let us take, because I've said it's a graph, so again, let me take in a C. And let us say the values which are possible for this one are a G and a B. Let's just take that. Now, the consistency that I'm considering is called as the edge consistency. So I look at each and individual edges and make that consistent. Also called as the arc consistency. Of course, also called as the two consistency for the same reasons. So let's apply this and see if we find that there's something wrong, if some of the domain values are just not possible, so I just delete them. And it turns out, yes, it is there. So if A takes red, B can take green, perfectly okay. Consider the reverse edge. If B takes green, A can take red. However, if B takes red, oh my god, there's no value of A possible. If this takes red, A cannot take red, they'll be the same color, so no value is possible. And because no value is possible, that's bad, and therefore I need to delete this up. And therefore we have ruled out one value from the domain of B. So let's do it one more time. This time I do it on the other edge, which is there, B and a C. So if B takes in a red, C takes in a G. If B takes in a G, C takes in a B. No problem. For whatever value B takes, C has at least one value. It's consistent. Let's do it the other way around. If C takes in G, B takes in R. If C takes in B, B takes in, it could take either R or a G. There's absolutely no problem. Two options. I just needed one. So this edge is consistent. This edge is consistent. So the only thing which is not consistent is this R over here. And therefore, because I've checked edge consistency and I've applied it over here, so let's, in a very triumphant manner, victoriously delete R because it's not possible. Now there's a problem. Let's, before we say that my graph is consistent, apply arc consistency on BC one more time, just to see if something changes. So let's apply it one more time. So let's consider C and let's consider a B and a C. If B takes in the value G, C takes in the value B, perfect. Okay, I'm doing okay, there's no problem. Let's do it the other way around. If C takes in a B, B takes in a G, okay. If C takes in a G, oh my god, B will not have any value. And what happened? Just because I made this consistent, this became inconsistent. So now I'll have to delete G and make it consistent. And who would have thought, I've got the solution right here, one value each, consistent with each other. When I initially drew this up, even I did not know that it's going to become a solution straight away from this. And of course, my inference will delete these values from the domains. Not only that, my inference, if something would have become null, so just imagine that this G wasn't, this B wasn't there in the graph originally, the value of the domain of this would have become null. And that's when I would have said, no point in going in. It is what is it is what is a step in which you will have to backtrack, either backtrack it right now or backtrack it later. So just delete B over here and repeat the same example. You will get an example where backtracking has to be enforced right now without even trying values for A, B, and C, because you know that there is nothing which is possible. So this one is called as the arc consistency algorithm. And of course, now I'll give you the actual implementation of this. So let's first write down an algorithm that makes a edge Vi, Vj consistent with, of course, the domains Vi and Vj. From Vi to Vj, a directed edge. So from Vi to Vj, a directed edge. Let's call this as make consistent edge. Okay, long name. So let's call this thing as make consistent edge. And all that I aim to do is that I aim to delete as many as values possible from Vi, those values for which Vj cannot take any value. So I try all values, so that small v in domain of Vi. So given the fact that Vi will take in a v if there exists at least one value w in domain of the variable j which is consistent with the assignment that I'm trying to make Vi is equal to v, then there is absolutely okay. There is no problem. However, if that is not a case, there is no assignment possible if Vi takes in the value v, then I have a problem that Vi cannot take in a value v. That means I have to delete v from d of v of I. And just delete it. It cannot take that value. Now, to my algorithm, I also need to return whether I'm making any change, whether I'm making any deletions or not, so that it knows about it. So let me say the variable or the flag deleted. Initially, nothing is deleted, and now something is deleted. And I just return deleted. It just tells you whether something was deleted or not. It just tells you that one thing. So that's what I call it as make consistent. It will make one edge consistent. Now, the obvious thing to say is, what is make consistent graph? Call make consistent edge on all the edges. The graph will become consistent? No. We only had a case making one graph edge as consistent, made the other edge as non-consistent. So what's a better algorithm for making graph consistent? Call make consistent edge on all the edges. If anything was deleted, restart the algorithm again. Call make consistent edge on all the edges. Now it turns out that this algorithm will of course have a slightly more computational overhead. There's slightly something that I can improve. So let me improve that one little thing. And before that, I make an observation from the problem itself. So my problem was that I had a Vi, Vj, that I made consistent by putting a few deletes over here. Now, by putting a few deletes over here, can I guess which edges will now possibly become inconsistent? The edge AB, which has nothing to do with these, will remain consistent because they were not relying on these values. So what are the edges that will now become affected because these values were selected? And that is any vertex Vk which had an edge on Vi or Vi's neighbors with the incoming edge. Because here I would have said if this takes this value, it takes this value, but now this value doesn't exist, so it may not be able to take that value, or this Vk Vi will become inconsistent. So saying if a V, any V is deleted from the edge Vi, Vj, if you do that, then all incoming edges Vk, Vi may now become inconsistent. And I need to make them consistent again. Now it's a simple algorithm. So have a bag, it doesn't matter which data structure you implement, have a bag full of edges which are potentially inconsistent. Take one out, make them consistent, take another out, make it consistent, take another one out, make it consistent. If by taking out a VI, you deleted something, then put all the neighbors, all the neighboring edges back into that bag so that you can just ensure again whether they are consistent or not. So the algorithm in this case is what is called as a AC3 algorithm. This 3 is the version number. So normally when I ask what is the AC3 algorithm, people are like, we've never heard about it, and especially the 3, it's the version number. It stands for Arc Consistency Tree Algorithm. Of course, it takes in a constraint graph which all the vertices, the edges, the domains as input, and all that it does is that it makes a queue. So the bag over here is a queue. You could take it whatever you want as the list of edges which are potentially not consistent. Initially, all edges in the constraint graph so initially all the edges are potentially not consistent, and I'll take one out of the queue, I will make it consistent, I'll throw it away. Simple algorithm. So while queue is not empty, all that you do is you take out a VI, VJ. So the top element in your queue, of course, you delete or you dequeue. Then you call the same upper function to make this thing consistent. So you call make consistent edge VI, VJ. If nothing was deleted, go ahead. Nothing was deleted. If something was deleted, then you need to add all VKVI to queue for all inbound edges. So eventually it may appear that the graph queue will grow with size, but later on deleting will not change anything. And you're done, you're consistent, you made everything up. In pursuit of doing that, if the domain of the variable becomes empty, you return that no solution possible, return failure, which I will denote it by a special term as false. And of course, you return true. It's not that when you return true, a solution will be possible in the branch. It's just that our consistency is not strong enough to find it. So that's an arc consistency algorithm. Simple enough. You just make a bag of all edges, you take them out and keep throwing them away. If you delete something, you add the neighbors. If the domain becomes empty, you know no solution is possible. If you're wondering what the complexity is, there are effectively two loops over here. This is what you see as the first loop, and this there exists is the second loop. They all go to the domain. Let's say that there are d values in the domain. So this is a d square operation. So now the complexity is OD square because of this times the number of times the make consistent algorithm is called. So initially it's called how many times? Initially it's called for all the edges which are there in your graph. So let us say that there are C edges which are there in the graph. So it's called C times D square. However, an edge after being made consistent can again come back. It can become inconsistent. After being made consistent again, can again come back. After being made consistent again, can again come back. Every time it comes back, one value is deleted. Every time it comes back, one value is deleted. So how many times can it come back? It can come back d times. Because after that, the domain will become empty. And that is what is the complexity, where this is because of the make consistent algorithm. This is because you are inserting every edge. And this is because number of times an edge can enter or exit the queue. So it is CD cube